Hey there, I'm Alejandro, and welcome back for day 245, me doing Daily LeetCode challenge. That's every 20 years worth of contributions here on GitHub. So today's problem is for March 18th, 2025, and without further ado, let's get straight into it. Okay, today we get LeetCode medium, problem 2401, longest nice subarray. You're given an array nums consisting of positive integers. We call a subarray of nums nice if the bitwise AND of every pair of elements that are in different positions in the subarray is equal to 0. Okay, seems like we're in a bitwise topic now, bit manipulation topic. We call a subarray nums nice if the bitwise AND of every pair of elements that are in different positions in the subarray is equal to 0. Length of the longest nice subarray. A subarray is a contiguous part of the array. Okay, subarrays, not subsequences. Note that subarrays of length 1 are always considered nice. Wait, okay. Subarray of nums nice if the big one's I see. Bitwise AND means that they must have wherever at least one for every single column. If we think of like the bits of a number as ones and zeros and we line up a bunch of numbers, it must be that at least one thing in the column is 0. Wouldn't it be like the length of the entire, like, yeah, why is it not like, wait, okay, no. Subarrays of length 1 are considered nice. I'm misunderstanding here. Bitwise AND of every pair of elements. So when you AND pairs of elements, not all the elements together, right? Otherwise, the best case would be, yeah, okay. I see. So here the longest subarray is 3, 8, 48. The subarray satisfies the condition. 3 and 8 is 0, 3 and 48 is 0, 8 and 48 is 0. Can't you just do some like sliding window logic for this? Right, once you find something that isn't valid, you want to make it valid again. Yeah, okay, what are the time constraints? Yeah, okay, you will have to do this in linear or n log n time. Maybe sorting the number, no, because we want direct subarrays, we don't want subsequences, that's not going to be that. We want the longest nice subarray. So this is an optimization problem at the end of the day, which usually means you can either do DP, greedy, or divide and conquer, right? In this case, what comes to mind is sliding window for me. There's going to be some way of essentially using the information of the fact that if everything has a bitwise value of AND, right? If I have a subarray A, B, C, and D, right? And I essentially have, and you know, let's do E, F, comma, dot, 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 comma, Z. And let's say that A and B equals 0, B and C equals 0, but C and D, say this also equals 0, but D and E doesn't equal 0. All right. Then essentially we say, okay, we have length 4 is good. So here we have L equals A, really, or A equals n 0. This is A in parentheses. R equals 0, 1, 2, 3, 4, which is really E. So then it's like, okay, current streak, longest streak so far is like equal to 3. We've had this streak of 3. Now we gotta break the 3, right? Does it mean that, like, this is what I mean. Does this mean that D will, or like E will break with every single one of them? And it's like you got to restart at E, or does it mean like, you know, you keep doing it until you find the very first one that works? And then once you find one that works, oh yeah, let's say with A it doesn't work. Let's say D and let's say, oh no. Oh no, wait, this is subarray, so you do have to restart at E, don't you? Right? Doesn't matter how many E is good with. The fact that it doesn't work with D, it just doesn't work. Is that really going to be it? Okay. Res initially equal to 0. Or over here we can say L is equal to 0 for R in range nums. Right, here we'll say curve streak is equal to 0. Arrange length of nums, obviously. Here we'll always say prev num is equal to 0, right? 0 and x equals 0 for any x. X and 0, any x by default. Okay. Here we can have a curse streak. If here we'll say for r comma num and enumerate nums, then we'll say prev num and num equals 0, valid case, continue building the window. So here we'll say curse streak plus or equal to 1, prev num is equal to num, res is equal to max of res and curse streak. Actually, we'll be able to set this otherwise, right? Here we'll say invalid case must restart the window. And now we'll say curse streak is equal to 1, prev num is equal to current num. We'll have a streak of 1 from that number onwards. And now res is equal to max of res comma curse streak in the beginning. That way we don't need it here. And then here we'll do something like return max of res comma curse streak, right? This is not necessarily a bit manipulation problem, is it? No, okay, so here I do get a wrong answer. Here I get an answer of 4. Okay. No matter what, I'm gonna set prev num is equal to num. Oh, if every pair of elements, right? Not just if the next to each other elements, right? 38 and 48. Yeah, so you still have to check 3 and 48. Ah, I see. I see what's happening here. You're face to face with greatness and it's strange. So what I need to do, yeah, what I actually need to do is I need to do prev num. What I really need to do is prev bits. Here what I need to do is prev num. We're going to do or equals num. Here we're going to set prev num just equal to num. Right? And that should be enough. Yeah, I see. No. Uh-oh. Wow. Okay. This is not going to be one of those, right? No. Maybe it's because I'm messing up at the beginning. Yeah, here I don't even need a current streak. Interesting. We passed 51 out of 65 cases. Ah, I see. Just by having everything like this, I might... Yeah, it makes sense. I'm making the restrictions too hard. I just need to make sure that it bitwise ends to 0 with everything in there. Okay. It needs the bitwise end with everything in there. But no, right? Like, every single step of the way, there cannot be any conflicting ones ever. You cannot have any conflicting bit once, right? Yeah, if no bits match, right? No bits match. Yeah, why doesn't this work? I'm actually kind of confused. This guy, 15. 1, 2, 3, 4, 5, 6, 7, 8. Oh, was this guy part of the previous window? Or something like that? And you got overshadowed? Oh yeah, no. So what we need to do is treat this like a sliding window problem. Yes, so my intuition was right at first, but for the wrong reasons. We need to keep shifting the window. Yeah, this is gonna make sense. We need to keep shifting the window. Yeah, otherwise, wrong. Shift the window till valid again. Prev num and num does equal 0. We'll put a continue. That way we can get out of the else clause here. Okay, let's shift this. Let's put this here. Valid again. Step 1, update res. Step 2, shrink window until valid. While prev num and num doesn't equal 0, we're gonna say we need to unor it, which I'm gonna guess means ending it, right? Here what we'll say is lnum is equal to nums, right? At index L. Prev num. How do I unset bits? I don't just end it. They're already set. Do I XOR? I XOR with it, right? Prev num XOR equal to lnum, right? Because everything except the 1 bits, those bits will be 1 inside of prev num because they've obviously included that number. So when I XOR 1 with 1s, they become zeros, and the zeros, if I XOR 0 with a 1, it stays a 1. If I XOR 0 with a 0, no, that's a problem. That's a problem. If I XOR 0 and 0, no, 0 and 0 stays together, right? 0 XOR 0 stays 0. 0 XOR 1. 0 XOR 1 is the issue. Or 1 XOR 0. Prev num, it might be zeros and ones. Lnum will be a bunch of zeros. Wherever lnum has a 1, prev num will have a 1. 1 XOR 1 turns into zeros like I want. Now lnum might have zeros, right? That's not gonna work. I don't want it to XOR the 1, so no. 0 XOR 1 is just 1. 0 XOR 0 is just 0, right? When you XOR anything by 0, it doesn't do anything. No, this is actually good. This is actually good. Okay. Well, prev num and num doesn't equal 0. Lnum, prev num, we're gonna XOR equal by lnum, so that we undo the effect of having or equaled by it. Here we're obviously going to say that L plus or equal to 1 and cur streak minus or equal streak minus or equal to 1. Really what's going to happen is like the size of the window is always going to be what it is. Right here we can insert r minus l plus 1 equals curve streak and assert it over here. Okay, maybe not over there. Over here. And we're going to relax with that. Okay, yeah. F string L equals R minus L plus 1 equals curve streak equals, might be off by 1 here. Yeah, sure. Ooh. L less than R and this. Okay, yeah, we might have a wrong solution for now. Here's double, that's really worrying. I mean, it should get to a point where if I delete everything, at most it should be going to index R. What? If I keep XORing element away. This is interesting. One to 4. Two, three, 4. Should be R minus L plus 1. Jeez, what is going on? I should even have to check for LNR. Like when it gets to R, it should have made prev num like 0. So 0 and num will definitely be 0. Yeah, this is not possible. What's the number of the next 4? 0, 1, 2, 3, 4. What the heck? Quark or prev num equals L to R. This one equals. Okay, this is what I want to investigate. Something like this. Python 3 prev num is equal to 56. So first of all, this should be the ORing of these, right? So 3 or 8 or 48 or 10. 59, but prev num is actually 56. It's 59 XOR 1. 59 XOR 1. It's just that. XOR 3. I see. So maybe I should start off prev num. For r in range 1, length of nums. Num equals nums of r. Nums of 0. Curse streak is equal to 1 maybe. Still the same thing. So it's like 8 or 48 or 10 is 58, or 3 is 59. 59 XOR 3 is 56. I could also just do it in terms of like, does bitwise ORing become the equivalent of actually adding the number, and that's another way to verify, right? Because if it added by that number, that means that a new bit was set everywhere. So really, it's just not including that 3 in there. Why is that? One XOR 3 is just 3. Or it's all just 59. This is the same check. Whoa. Okay, that's weird. I don't know why the battery went out. Oh, there we go. Okay. Curse streak. Yeah, we really don't need a current streak anymore. Maybe that should be on myself from now on. Yeah, because the current R is invalid, right? That's the point. So yeah, we fix that case. On myself. Sweet. 5 or 11 or 13. But I'm saying prevnum is 4. Why? What was before 5? What? How do I even get 4? 4 is 1, 0, 0. Right, if I do 5x 11, if I do or 30, yeah, okay, 5 or 11, add to 15 XOR with 11. Oh, it just doesn't give me back that 5. It's not really an undo operation. Yeah, it's not really an undo operation. Well, okay, what I can do is in terms of sum of numbers, right? I could do it in terms of sum of numbers, because whenever you, you can do it in terms of sum of numbers, because then you can check, does bitwise ORing become the same thing as, there you go. Cursum, we'll call it cursum. If otherwise prevnum and num is equal to 0. I just want to make sure that this is the same condition. Yeah, we can deal with things in terms of sums. It's actually going to make things a lot easier. Here we're going to do prevnum minus or equal to lnum. This is actually going to be really nice. Really now. All right. String prevnum equals cursum equals num equals. Okay. Maybe that's why. This should be 0, 0. For r, num and enumerate nums. There we go. Okay. Why is prevnum and cursum not the same? Here I'm doing cursum. Yeah, I'm gonna have to forget about this. Okay, I'm gonna have to forget about the prevnum stuff. Yep, I'm just gonna have to forget about the prevnum stuff. Yeah, for now, let's just comment this out. Comment this out. Let's just forget about prevnum. Yep, okay. Here we say curse sum, while it's not the case that curse sum or num equals to curse sum plus num doesn't equal to, yeah, something like this. I mean, this is the part I just don't get. Like, eventually, I'll get to a curse sum of 0, man, right? And 0 or something will definitely equal to 0 plus that something. Two to 4. 5, 11, 13. Why the heck is the current sum 4? Current sum, I am adding, right? Yes. Current sum 0, I'm always going to add a number while it is possible. Otherwise, when it's no longer possible, we're going to keep subtracting from current sum. I mean, I'll put a while L less than R, but I should get to the point where it's 0, man. A negative curse sum, what the heck? Dude, that's not possible. I'm subtracting numbers I added, man. Well, I guess here I gotta add 1 to num. L equals R. Equals 0, man. Wait, okay, I'm gonna kind of lose it here. Okay, we're gonna restart. Well, actually, okay, no. I'm only gonna use things I need. We're gonna assert that's specifically less than. Is it because we're gonna get to the point? interested in these finals. This is for case 2, right? How the hell is the current sum 4? What? Not crazy here. L, yeah. Okay, I'm gonna delete anything I don't need. Don't need this. Don't need this. Okay, res L is 0. Current sum. Alright. The thing is we need to add our what we need to do is add R to the window. But we really only want to do it if it's valid. Is it just that I just don't do something like this here? Is it just something as simple as this? Oh my goodness, no way. Okay, no. There's other cases we fail. Really, it could be something as simple as this. No. Or it could be that this should be +1 over here, because here we're including the last element. Yeah, okay. It is just as simple, isn't it? Output limit exceeded. Prints will become hashtag prints. Okay. Okay, I actually am a huge goof, but there we go. Completion streak 245 days. Consistency is key. See ya tomorrow. Okay. I was never actually putting num into the window once I fixed the window. Okay. The prev num solution could have probably worked. Actually no. We're realizing XOR doesn't have that nice backwards compatibility. Okay, you know what? There we go. Bada bing, bada boom. That is enough work. Okay, we can that. Slide window from the left until valid again. Yeah. Here we'll have is valid equals to this. If is valid, cursum Let's just keep that. Don't fix what ain't broken. Not +1 since num broke this window. Step 3, add num to now valid window. And there we go. And then here we'll say res less than or myself, or myself. There you go. Okay, beautiful. And there we go, 86 ms, speed 77.74%. That is absolutely what we love to see. So there we go. So nevertheless, as always in all my videos, I do a quick recap of how I solve the problem. So for this one, it was a little bit of a challenge. Although I was really just making a goofball mistake of never adding num back to the window. That's my fault. But essentially, oh my gosh, a voice crack right there. But essentially, you're given an array nums consisting of positive integers. We call a subarray of nums nice if the bitwise end of every pair in that subarray is equal to 0. Return the length of the longest nice subarray, right? And so it must mean, like, for example, if you have 3, 8, and 48, my first mistake was thinking like, oh, it just means that 3 and 8 must be bitwise end of 0, and 8 and 48 must be bitwise end of 0. No, 3 and 48 must also be bitwise end of 0. It's every single pair inside of the subarray, right? And so my idea was this: since we don't want just, you know, the ands of every single thing inside the array, I wanted to use the sliding window approach for this problem just because it felt very intuitive, and also I realized, like, you know, the constraints do not allow for an n-squared solution. Otherwise, like, you know, it's very, very, it'll be much easier to, you know, just go through all the pairs, and there you go, right? Although for something like that, you might even need an n-cube solution and so on, but, you know, so some way to figure it out. But, so what I realized is, like, okay, ideally we do this as kind of a sliding window approach, but the caveat is that whenever we break the window, like, we need to make sure that, you know, whenever we add a new element to the window, is it valid with every single element currently in the window? And that would be an O of n operation. And if we're doing O of n total calls and in each subcall up to O of n work, then that's an O of n squared algorithm, and that's no bueno. So we need an O of 1 way of checking whether adding an element breaks or makes the current window, right? And so we need to check whenever we add an element, is its bitwise end with every element beforehand equal to 0, right? And the way that I did this is essentially realizing that, okay, if I always have access to the bitwise OR of all the elements in my window, and then I take the AND of that with another number, and that happens to be 0, then I know that that number's bitwise end with everything in there is definitely 0, right? The reason being is, like, you know, suppose we have a couple numbers, right? Let's say we'll put them in terms of bits here. We'll have, you know, 0, 1, 0, 1, 1, 0. Here we'll have, you know, 1, 0, 1, 0, 0, 0, right? And we know that the bitwise end of these guys is going to be, well, 0 and 1 is 0, 1, 0, 0, 0, 0, 0, 0. Okay, this is 0, which is valid, right? And now we have a new number, and we want to check if its bitwise end is also 0, right? And, like, you know, let's check that, like, you know, the whole number like this. Well, again, remember, we don't want to just bitwise end it with every single number that's currently in our window. Let's pretend that there's these two numbers in our window at the moment. We want to do this in O of 1 time. So what we can do is take the bitwise OR of these numbers, right? Which will then be, right, this was the AND. Now let's do the OR. This will be, okay, let's take the bitwise OR, right? Here we'll do 1. This will be 1, 1, 1, 1, 0, right? And when we take the bitwise OR, right, we'll see, you know, wherever there used to be a 1, right? And we must check that, okay, the current number that we have, it must be that when we end it with every single number in here, it has a bitwise end of 0, right? So if we take the ORing of all the elements, we'll essentially figure out where all the spots where there was a bitwise 1, right? And so it must mean that whatever number we have, it must have a bitwise end of 0 with every number. So we need to know where all the bitwise 1s of every number was and then bitwise and make sure that, you know, we have a 0 at every single one of those spots, right? So if we bitwise OR all the elements that we have in our current window, we'll have essentially a number that where, you know, you'll have ones activated wherever there's a 1 in any of the numbers, right? For example, here it happened to be in the second number, but here it happened to be in the first number, right? But the point is that these are both 1s because there was at least one number that had that 1, right? The only one that is a 0 is because it was a 0 in every single number in the window. And so that way we can check, like, whenever we add a number, it's like, okay, is it bitwise and against the bitwise OR of all the numbers in the current window, does this produce a bitwise AND of 0, right? And in this case, it does, right? This will be 0, 0, 0, 0, 0, and that means we can add it to the current window. Now, there are some issues with this, and specifically one issue, which is what happens when you have an invalid window and you want to take out elements from the left, right? And here is where I kind of struggled, where my first thought was like, okay, what if I XOR elements from the left, right? And I figured that, you know, this might work just because, well, first of all, you know, if I want to undo this number, right? Now let's say, like, you know, the bitwise OR that we have over here, after we have everything, will be just a bunch of 1s, right? Let's see if we want to get rid of this number, what happens? Well, if we get rid of this number, right, and let's say we're XORing here, so I'll make these, you know, XORs like this, then this will be 1 and 0 becomes 1, 0, 1, 0, 0, 1, right? And then it's like, okay, is this equal to the bitwise OR of this number and this number, right? And let's check. Here we're going to do ORs, right? And so here it's like 1, 0, 0, 0, 1, right? And it's like, oh my goodness, this actually works, right? But this is a perfect example where you have a bunch of 1s. And, you know, my ideology is like, you know, wherever the 1s are, I'm essentially going to unset them. And since, you know, we have a bitwise AND, we was always 0, like, you know, we don't have to worry about, like, you know, how many bits actually set that 1. We know that it's always 1 and so on. So to me, you know, XORing from the left seemed very, very promising, and it might work and so on. It's just that there were some cases where it wasn't actually true, right? If I do a 5 OR with 11, right, and then I do, okay, let me take that value of 15 and let me XOR it with 5 real quick, we'll get 10. We won't get 11 back, right? So there is a little bit of lossy information there. We could play around with the bits and so on, but XORing, turns out, is not enough to get back to the original state. And so then I got to thinking, and then realized, like, hey, if I'm going to always only allow myself to, like, you know, add numbers such that the bitwise AND of that number and every other number before it is 0, that means whatever number I'm trying to add to my current window, it must have 1 bits set at places where they've never been set before, which means that I can think of it as adding that number, right? Because since I'm going to be setting only 0s to 1s and not, like, you know, 1s keeping them as 1s, right? I'm always going to add by the full value of that number, right? For example, if I do 8 or 1 here, it's going to be 9, which is the same thing as 8 plus 1, right? But if I did 9 or 1, it would stay as 9. Why? Well, because since 9 is odd, the last bit, the least significant bit, will be set. So when we do 9 or 1, right, both of those bits are set, so it stays that way. But for 8, it's an even number that the least significant bit is a 0, right? And since here, you know, 1 only has 1 bit, which is the least significant bit, and it wasn't set in 8, right, we're setting that bit in there, and so it'll be the full effect as if though we were taking 8 plus 1, which is equal to 9, right? And you can take more extreme cases, right? 999, or let's do even numbers, right? Yeah, so that those bits are set, right? So any number really, where it's not the 3 isn't set, right? Okay. 992 maybe, 991, right? Okay. I can't think of a number just yet. Maybe 1,000. Yeah, so 1,000 is not divisible by 3, right? And so, you know, it just didn't have the last 2 bits set. And since it didn't have the last 2 bits set, it's as if though we added by 3, right? So instead of checking if, you know, a number and, you know, I can check if a number and the bitwise OR of all the previous number is equal to 0, and that will be enough of a condition. The only problem is when we want to shrink our window from the left, we need a way of undoing those bitwise ORs from the total bitwise OR of our current window, right? And I thought XOR would help me out, and maybe there is a way of doing it. that I didn't think about, but I thought of something even better. Since we can think of it as whenever we add a number whose bitwise end is 0 with all the numbers in our current window, we can think of that as adding to the current sum of the numbers that we have, right? And so that's exactly what I did. And instead of checking if a number the bitwise end of all the numbers in my window bitwise ORed together is equal to 0, I can just check, okay, the current sum of the numbers in my window, if I were to OR it with num, would it give me cur_sum plus num, right? Because if it gave me cur_sum plus num, remember all the numbers are positive here. If these two things are equal, that means that num, all the 1 bits inside of nums activated were 0 bits inside of the current sum number, right? The current sum is the number is all the numbers of my current window summed together. And if ORing this with num is the same thing as current sum plus num, that means that all the 1 bits in nums must have been 0 bits in cur_sum, such that when I ORed them together, right, they all got set inside of cur_sum, and so that way this is now equal to whatever the value is of cur_sum plus num. So if I check for this, that means, okay, it must have meant that the bitwise end of num with every single number in my current window is equal to 0, right? Because by this check, right, since this is equal, this will always be less than or equal, right? But if it's strictly equal, that means it's like, okay, this set, all the 1 bits in here must have been 0 bits in here, right? Since this is the sum of all the numbers before, right? That means it must have been the 1 bits inside of this number num must have been 0 bits inside of every single number in my current window, because here's the current sum of all the numbers in my window, ORing it with num, bitwise ORing it with num is actually the same result as cur_sum plus num. So again, all the 1 bits in here must have been 0 bits in here. So here it's like, okay, this is a valid case. I could just add by num, right? Whether I add or bitwise OR, it doesn't really matter, right? Maybe this gets me a little bit of a faster solution. That would be kind of cool. Ooh, it actually does, and kind of nice, very nice, very nice. As is actually kind of nice. There we go. So yeah, we can remove that for now. Damn. All right, 77 ms. Very nice, very nice, very cool. Okay, but that is pretty much all, right? So here we'll say, okay, cool. Adding num to our current sum works just fine. Cur_sum or num is equal to cur_sum plus num. So let's just add it to the current sum. There we go. Bada bing, bada boom, chop chop, and then just continue with the for loop, right? We just kept increasing our window. Then at some point, unfortunately, or if it happens at all, but probably will, is that we reach an invalid window, right? Adding the current num will not have the same effect as ORing it, which means that there's a conflict with at least one of the bits out of one of the numbers somewhere, right? So we need to keep shrinking our window from the left until it's valid, right? Well, first things first, right? The current size of the window is always r minus l plus 1, right? Adding the number at index r just broke the window, so we can't include that one, right? So the current window size is r minus l plus 1, but the one at index r just broke the window, so we can't include it, so minus 1, while 1 minus 1 is just 0, so this is r minus l total window numbers in the window that were actually good, right? So if res is smaller than r minus l, then let's set res to r minus l, right? Because we want the longest possible valid window. So that's all we're doing, and now let's actually shrink the window until it's valid again, right? Again, the way we're gonna check is valid is like always checking, okay, does cur_sum ORed with num equal to cur_sum plus num, because that would mean that num, all the 1 bits instead of num are essentially 0 bits in the cur_sum, right? While this is not the case, let's keep getting rid of numbers from the left of our window. And remember, we're using a current sum here. We're not using a bitwise OR of all the numbers. We're using the sum of the numbers and kind of abusing that property. And so here we're going to subtract by nums at index l, l plus or equal to 1, and keep doing this, keep getting rid of the numbers from the left-hand side until we get to a point where adding it would be valid, right? And once that's the case, then we're like, great, adding the number is valid. Let's actually add the number into the window now. This was actually my mistake. And then just continue the problem from then on, all right? And at the very end, we'll just keep doing this over and over. And at the very end, it could just be that, like, we got to a point where, the remaining elements inside of the window is indeed... well, yeah, it could be like, the best solution is at the very end. So it's like, if I just do return res, I will probably get a wrong solution. well, maybe not in these test cases, but in somewhere else. Yeah, so like this test case, for example. So yeah, here we just need to make sure that it's like, okay, you know, the best answer could be at the very end of the array. So it's like, you know, if it's at the very end of the array, like you'll realize all we do is like, you know, keep doing this over and over and over and over and over, but we never actually get to the point where we set res again. So it's just at the very end, it's just like, you know, if the optimal answer happened to be at the end, let's just take the max between the current best thing we found and the solution at the end, right? It just could be that L is right at R, so this happens to be like 1, right? And so, but whatever it is, we'll just take the max of these two, right? It's just more often than not, it will probably be in res. If the solution is not at the very end at the end of the array, right? But that's pretty much it. And yeah, and as we can see, it is a very nice, crispy, and efficient solution, which feels absolutely awesome sauce. And yeah, so hopefully that solution makes sense. But otherwise, that's pretty much it for this video. If you did find it useful and enjoyable in any way, shape, or form, I'd highly appreciate if you left a like or comment. But otherwise, I'll catch you in the next one. So till then, ciao, ciao, my friend. Bye-bye.